In Chapter 16, we'll be talking mainly about buffers and titrations. Buffers are important to biological solutions because we need the pH to stay constant. Any change in pH can have a detrimental health effect. And more than that, if pH is not maintained for some reason, then there is a pathological condition. I misspelled that. Condition. Specifically, if we're looking at humans, the average pH of blood is equal to 7.42. Less than 7.42. If the pH is less than 7.42, then this is called acidosis. If pH is greater than 7.42, then this is alkalosis. And I misspelled that. Let me rewrite alkalosis. And the blood must be buffered or it can cause death. Typically, we see two different types of situations. We can see respiratory problems. We can see metabolic problems, or more specifically, in times when the liver or lungs are not functioning properly. So let's go ahead and take a look at what constitutes a buffer and some beginning definitions. The purpose of a buffer is to maintain pH. That doesn't mean that it is neutral. Not necessarily neutral. It really just depends on the system that we're talking about. For example, in human health, the stomach, the liver, the small intestines, and the blood will all have different optimum pHs. Right, so if we're looking at a buffer system, we would expect to see an acid, a conjugate base, in some sort of aqueous environment. All right, so it is a solution or a mixture. That is, there's more than one type of compound or element. Let's go ahead and formally define these terms. Buffer, as I said, is a mixture or solution of a conjugate base, acid, pair. One of the things that you've seen in lab is titration. And titrations are lab methods to determine the concentration of an unknown. And for the past couple of weeks, you've been working with acid-base solutions. Next, an indicator is a dye which visually indicates a change in pH by color. And you guys did this with indicators where I believe you had to identify the unknown indicator. Lastly, the equivalence point is the moles of a standard solution equal to the moles of an unknown solution. So we look for the equivalence point and then we can identify that concentration. Equivalence point, and then we identify the concentration by a series of calculations. We've stated previously that a buffer is a mixture of the conjugate base and acid, mixture of conjugate base, which will abbreviate CB, and acid, which will abbreviate with a big A. We need a mixture because to maintain pH, if a strong base is added, we want our acid to neutralize it. And if we have a strong acid added, we want our conjugate base to neutralize. See if I can move that up there for a second. Okay, so shown up here in our picture, we have a pH meter and different solutions. The first solution here is our acid, and you can see it has a pH of 2.9. That makes it a weak acid. The second picture shows sodium acetate, which is the conjugate base, and it has a pH of 8.9. So let me go ahead and mark those. That's the acid, that's the conjugate base. I can tell by the pH. When they're mixed together, when I have an equal amount of both, then the pH is 4.7. Okay, so drawing some reactions here. If we have acetic acid, HC2H3O2 plus hydroxide coming from somewhere. This will react to produce C2H3O2 negative plus water. Okay, so when water is the product, that means we have neutralized it. So we have our strong base and our acid component neutralizing it by producing water. Likewise, if we add a strong acid, then the sodium acetate component plus hydronium will give us HC2H3O2 plus sodium. Right, so in this case we had a strong acid added to our conjugate base, and we have neutralized it by producing the acid again and the salt. So another way to look at this is that buffers consume acids and bases that are added to whatever solution. And in that way, they maintain the pH. In this case, they would maintain the pH around 5. Remember, it does not have to be neutral. Another equation that we use a lot of times in calculating amounts or pHs of buffers is the Henderson-Hasselbalch equation. And you will see this again if you take analytical chemistry or biochemistry. The equation is pH is equal to pKa plus log of the conjugate base concentration over acid concentration. So pH we know, and we know conjugate base and acid, but we do not know pKa. Anytime you see a little p in these sorts of calculations, it means negative log. So pKa is equal to the negative log of Ka, just like pH is equal to the negative log of hydronium. We looked at Ka in chapter 15, so we know that as Ka increases, pH decreases. Well, adding this term pKa, as the pKa decreases, because it's the negative log, it's the opposite, pH, or the strength of the acid, also decreases. All right, so let's look at 4 examples. We're going to work some problems with the Henderson-Hasselbalch in just a minute, but let's look at how to calculate pKa. We have 4 different combinations, A, B, C, D, or buffer pairs. And we're given the Ka, and we're going to solve for pKa. Right, the first buffer pair is potassium acetate and acetic acid. Remember, this is a pair, so we have 2 things we're considering. The second one is NH4 ammonium chloride to ammonia. The third one is potassium hypochlorite, ClO2 to HClO2, and then the hypochlorous, potassium ClO to HClO. All right, I looked up on the chart in the book the Ka values. 1.8 times 10 to the negative 5th. The next one is 5.6 times 10 to the negative 10th. The third one is 1.1 times 10 to the negative 2nd. And lastly, 2.9 times 10 to the negative 8th. I can tell which one is the strongest acid because it has the largest Ka, and that is this one, the HClO2. Right, now I just plug and chug. I put in negative log of the Ka and the pKa. Remember, it should be close to 5. When I calculate it, I get 4.74. Okay, the second example, negative log of 5.6 times 10 to the negative 10th is 9.25. The third example, negative log of 1.1 times 10 to the negative 2nd. Again, it should be close to 2, and it is 1.96. And lastly, this one should be close to 8. Negative log of 2.9 times 10 to the negative 8th is 7.54. We're going to use these pKa values here on the next slide when we one of the next slides when we calculate the ratio of conjugate base to acid pair. All right, here's our first example problem. We're going to use the Henderson-Hasselbalch formula to calculate the ratio of conjugate base to acid. And in this case, we want the ratio to know which one is the best buffer at a given pH. In this case, we want to know the best buffer at 7.20. We want that ratio of conjugate base to acid to be as close to 1 as possible, 1 or less. All right, so we're going to plug and chug and solve for conjugate base to acid ratio. The first one, which was potassium acetate to acetic acid, C2H3O2. And I know that pKa for this one is equal to 4.74. Okay, so we're going to plug and chug. 7.20 is equal to 4.74 plus log, and I'm just going to abbreviate base to acid there, minus 4.74 from both sides. So when I subtract, I get 2.46 is equal to log of our ratio of base to acid. And then if I divide both sides by log, that is the same as taking the inverse log or using the 10 to the x. Okay, so when I do that, okay, marking those out, that is 10 raised to 2.46 is equal to the ratio of base to acid. And when I solve that, it is 288. When we write a ratio 288 to 1, that's the same as saying that. Okay, let's move this up and look at letter B. B. And this one is the ammonium chloride ammonia mixture. And pKa was equal to 9.25. And so I put in my numbers. 7.20 is equal to 9.25 plus log of base over acid. 7.20 minus 9.25 is negative 2.05 is equal to log of base to acid. And so that becomes 10 to the negative 2.05 is equal to my ratio of base to acid. When I calculate that, that is equal to 8.91 times 10 to the negative third to 1. All right, let me erase for a minute. Well, it's not letting me erase. Let's see here. It still does not want to let me erase. Okay, I'm just going to move that up. I apologize. I know it's sloppy looking at it like that. All right, so letter C. See if I can write this small. C has a pKa of 1.96. So we've got 7.20 is equal to 1.96 plus log base to acid. And 7.2 minus 1.96, what we end up with is 10 raised to 5.24 is equal to base to acid, and that is equal to 1.74 times 10 to the fifth to 1. And then lastly, letter D, we have 7.20 is equal to 7.54 plus log base to acid. And I subtract 7.54 from both sides, and I get negative 0.34. So 10 to the negative 0.34 is equal to the ratio of base to acid. And when I resolve that, it's 0.46 to 1. Okay, so I know that letter D is my best buffer because this gives me the smallest ratio. So KClO / HClO are my best buffer pair for this pH. In the last two problems, we're going to be looking at titrations. And you guys have done this in lab. You know that you put either the strong base, the strong acid, either the acid or base goes into the burette, and then the opposite goes into the beaker. You drop, in this case, the sodium hydroxide into the beaker, and we use our pH meter to graph what we call the pH dependence. From there, we can find the equivalence point, and it's shown there in kind of small print. And the equivalence point is where we know we have an equal number of moles. And so we can find the volume there and solve for concentration, solve for molarity. But there's also something, the half equivalency point. And this is equal to 1/2 the volume of the equivalency point. And more importantly, this is defined as the place where pH is equal to pKa. And it's important because this is the buffering capacity. This defines where the buffering is occurring. Once we get beyond the equivalency point, then the buffer it has reached its maximum, and from there the pH will continue to go up or go down. So we have reacted, let me just draw this up here, we have reacted all of the buffer components beyond that point. So let's take a look at two titrations and define these terms on those graphs. Right, on this particular graph, we want to define the equivalency point and the half equivalency point, where the buffering capacity is, and we want to look at the pH of where we start and end. All right, first, the equivalency point, and that is marked here on the graph, and we just extrapolate over and down to determine our pH and our volume at that equivalence point. And so the pH is about 7, and the volume of base added is about 50 milliliters. All right, so we would use that to do our calculations if we were trying to determine concentration of the unknown. The half equivalency point is 1/2 the volume of the equivalency point. So this would be at 25 milliliters. So I would extrapolate over, this is 10, this is 20, and there's 25, and so I would go up to my line there and across, and that would show me where the half equivalency point is. More importantly, is this range is my buffering capacity here, where I know that my buffer is working and it's maintaining the pH, and you can see that the pH stays pretty constant there. Right, the pH at the start is about 1, and the pH at the end is maybe 12.5 or close to 13. I know that this is a strong acid because dilute solutions of strong acids are going to have a pH of equal to 0 or 1, and we can see that that is where we begin. I know that this one is a strong base because strong bases should have a pH of 13 to 14, okay? And it goes up just a little bit, but typically we may cut off our titration before we get to what that endpoint would actually be. Right, so in this case, I know that my sodium hydroxide is in the burette, and my hydrochloric acid or whatever strong acid I'm using is in the beaker. Lastly, let's take a look at another graphing example. Strong base and strong acid. In this case, we know that our strong base, our strong base is in the beaker and our strong acid, in this case HCl, is in the burette. I can tell that they are a strong base. If I look at where I start, the pH is equal to about 13, maybe a little higher than that at the start of the titration. And pH is equal to 1 at the end of the titration. So again, that tells me a strong base and strong acid. How would this look different if it was a weak acid and weak base? A weak acid, the starting pH could be anywhere from a 2 to a 4, and a weak base anywhere from an 8 to a 10. So I can tell the difference based on the pH values of where I start and end. Our equivalence point is at a pH of 7 here, and volume for this one is about 25. So pH 7 at 25 milliliters of HCl. And our half equivalency point then would be at 12.5 mils of HCl. So I would find that's about right there, and extrapolating a little bit over, maybe 12.5 pH is equal to 12.5. And I see my buffering region here where the pH is maintained. Right, in example 16.1 in class, the activity will be doing problems like we did on these last 3 slides, where you'll be calculating the ratio of conjugate base to acid and then looking at a graph and identifying these points.